looking at number 10 from the free response packet. So, a container has the shape of a right circular cone as shown in the figure above. The height of the container, so actually before we move on, this is important. It is a right circular cone, which means that if I were to draw a triangle through that vertex, this triangle would be a right triangle. That's important because any triangle that, so as the height changes, let's say the height is this, that's really hard to see. Let's do it in orange. That's probably terrible to see too. Let's do it in purple. Let's say the height was this purple line right here. Then the triangle that's formed from that purple line would also be a right triangle. Therefore, purple triangle and red triangle are similar triangles. That's going to be important later on, so keep track of that. Next, we are also told that the depth h is changing at a constant rate of -0.3 centimeters per hour. So the depth is changing. That's the rate of change of the height. So we can say dh dt equals -0.3 centimeters per hour. That's what we are given. So part A, find the volume of the water in the container when h equals 5. Indicate units of measure. Let's see what we got. I want to find the volume of the water. So the volume, as they told us, is 1/3 pi r squared times h. Problem, as you can probably see right off the bat. We know what h is. H is 5, but what is r? Well, not quite sure. We could figure it out, but I'm going to use the fact that I'm going to write an equation that relates r and h. And since these are similar triangles, we'll note that r is always 1/2 of h. So r equals 1/2 h. That constant is always the same, right? So now what we can do is we can replace r with that. So I get 1/3 pi r squared, which is 1/2 h times h. And this gives us, squared. So that gives us 1/3, so that's 1/3 times pi times 1/4. H squared times h is h cubed, and that cleans up to 1/12 pi h cubed. Okay, next we're going to take this equation right here, and I'm going to highlight it for now because it's actually a pretty important one. I'm going to take this and I'm going to evaluate it at 5, when the height is 5. And that's going to equal 125 over 12 pi. And that's our volume when the height is 5. And our units, because this is a volume at position, it is centimeters cubed. Next, part B, they want us to find the rate of change of the volume when the height is 5. So I'm going to take this highlighted piece right here. I'm going to take this and use it because this is my volume function, and it's all in terms of h, which is good. I don't want this in multiple variables, right? I want this in few variables as I can make it. And since I can get rid of r, I will. So let's take that and use it for part B. So for part B, we know that the volume equals 1/12 pi h cubed. And we were asked to find the rate of change of the volume. So we're going to, with respect to time. So we're going to take the derivative with respect to time to both sides. So we get dv dt equals 1/12 pi times the derivative of h cubed, which is 3h squared, times the derivative of h, which is dh dt. Now that dh dt is a constant, So what I'm going to do at this point is well, we're asked to find the rate of change of the volume. So I'm going to do this in 2 steps because I can use it because I know where C is going. But normally at this point, right, I could just start plugging in all my numbers. But I'm not going to do that right now just because, like I said, I know where C is going and I want to do some of that work now. So I'm going to replace dH/dt with -3/10. Again, normally I would replace everything at this point, but I'm not going to do it right now. So this is times -3/10, and this gives us -9 over 120. Is that right? Yeah. Actually, well, yeah, that's fine. So that gives us -9 over 120 pi h squared, which reduces to, let's see, what is that? Looks like 3 over 40. So -3 over 40 pi h squared. Again, I don't need to do this in 2 separate pieces. I'm doing this because I know that I'm going to need this a little bit later, and I wanted to kind of get that out of the way. Now, let's take this and actually replace 5. Let's plug in 5 for h. So we get dv dt equals -3 over 40 pi times 5 squared. 5 squared is 25 times 3 is -75 over 40 pi. And that's the rate of our change of our volume. So that's going to be centimeters cubed. Ooh, that's a terrible 3 per hour. So before I leave B, I do want to emphasize, if I had wanted to, and again, the reason I did what I did is I wanted this equation right here, because again, I knew where I was going to go with letter C. But if I had wanted to, from here, I could have put in my h equals 5 and my -3/10. Okay, so going from here to here, I could have plugged in all my constants at this time and solved, which would have made things a little bit easier. But like I said, I wanted the red highlighted formula. And here's why. The red highlighted formula, let's go to it. So I'm going to grab it and move it up. Now they're on to letter C. That's the rate of change of the volume. And they're telling us that the rate of change of the volume is proportional or directly proportional, right? It is directly proportional to the exposed surface area of the water. So looking at our cone, that exposed surface area of the water, they're talking about this right here. That's a circle. So what they're saying is the rate of change of the volume, dV dt, is directly proportional to that circle. Because again, the surface area of that water is a circle. So when we say something's directly proportional, remember what that means. It means we have some constant of proportionality times whatever we're looking at, in this case, A. Okay, that's what it means to be directly proportional. From here, we're just going to start solving. So let's see what we have. First off, we know that dV dt happens to equal -3 over 40 pi h squared. We also know that the circle equals pi r squared, right? The area of a circle is equal to pi r squared. But again, I don't want things in terms of r. So I'm going to use this again, and I'm going to get rid of my r's. So I get -3 over 40 pi h squared equals k times pi times 1/2 h squared. Let's just double check that before we move on to make sure everything looks good. It does. So going from here, I get -3 over 40 pi h squared equals k times pi times 1/4 h squared. So simplifying that left-hand side, we get, looks like k over 4 pi h squared. Now we have to solve for k. So let's do that. Let's see. Pi's cancel on both sides. H squared cancels on both sides. Excuse me. I'm going to multiply 4 to both sides, so I get -3/10 equals k. So before I finish this one up, I want to make sure we understand what we wanted to show here. There were two important things. One, they asked us to show, right? They asked us to show that the rate of change of the volume in the water is directly proportional to the exposed surface area. Notice that's what we did here. This line right here, that's a light color. This line right here is where I did that, because notice this is going to be, this is right here, some constant times h squared. This right here, I know it's hard to see because that h squared hasn't been taken care of, but that's going to be some constant times h squared. So they are related, except they are the same thing, except that we have this k constant, which we don't know at that time. And that's where we solve from there. That's number 10.